My PhD thesis is about effectively going beyond the standard model, and in this thesis I explored a new way using the standard model effective field theory to look for deviations of new physics in the data that we collected at the ATLAS experiment. So here we have the standard model particle physics, which explains nature at the most fundamental scale. Even though we know that the standard model is incomplete, it does not give us a way to extend it. To extend the standard model, we need to introduce measurable parameters, which we can then go ahead and measure in particle colliders such as the Large Hadron Collider. So one way, which has been quite popular in the past decade, is to look for direct production of new particles. Given that we have not seen any new particle yet, new particles are much heavier to be produced within the direct energy reach of the LHC. So in this case, the deviations from the standard model would appear in a subtle way across many different distributions. The theoretical prescription is given by the standard model effective field theory, where you write the Lagrangian, which describes the dynamics of how the fundamental particles interact, by the standard model Lagrangian and a series of higher order terms. So the standard model Lagrangian does not have a dependence on lambda, which is the scale at which we expect heavy new physics to exist. Rather, it is the higher order terms which are suppressed by lambda, which are actually sensitive to the scale of new physics. And our goal in my thesis is to try to uncover signs of new physics in these higher order terms, specifically the dimension 6 operators, which are relevant for measurements performed at the Large Hadron Collider. We make use of Higgs boson measurements from the ATLAS experiment. Since its discovery in 2012, we have collected as many as 30 times more Higgs bosons, and this allows us to perform a detailed kinematic study of its properties. Using this data, we are now able to constrain 19 parameters in the SMEF parameter space. 0 represents the standard model, and we expect that any signs of new physics would appear as a pattern of deviations across the standard model. Currently, we see that the measurements are not precise enough to uncover signs of new physics. This requires an expanded study taking into account measurements from other physics sectors. Currently, we see no obvious pattern of deviation from the standard model. However, with more data and an expanded set of measurements, we would be able to probe this parameter space in a precise way, which will allow us to uncover the footprints of new physics.